Hi everyone, I'm Dan Fullerton. Today's lesson is on pressure and Pascal's principle. Objectives are going to be to calculate pressure as the force a system exerts over an area, to explain the difference between gauge pressure and absolute pressure, and finally to explain the operation of a hydraulic system as a function of equal pressure throughout a fluid. So let's start by talking about what is pressure. Well, pressure is the effect of a force acting upon a surface. It's a scalar, it's a force per unit area, and its units are newtons per meter squared, or pascals, PA. Now, if pressure is force over area, we also have to remember that the force is always perpendicular to the surface. Now, when we're applying pressure, we have to remember that all states of matter can exert pressure. When you walk across an ice-covered lake, for example, you exert pressure on the ice equal to your weight divided by the area which contacts the ice. Example, you want to spread your weight out to avoid cracking the ice, to reduce the pressure at any given point. If you walk on snow with snowshoes, you have a large area of contact. That spreads out the force and lowers the pressure at any given point and allows you to walk on top of the snow. Now, fluids exert outward pressure in all directions on the sides of any container that's holding the fluid. Earth's atmosphere also exerts pressure. Atmospheric pressure is about 100,000 pascals, or 10 newtons per square centimeter. That's known as atmospheric pressure. You can experience the change in atmospheric pressure when you ride in an airplane and you change altitudes. You may experience a popping sensation in your ears as the pressure outside and inside finds ways to equalize. Let's talk about a sample problem where we're looking at pressure on a keyboard. Air pressure is approximately 100,000 pascals. What force is exerted on your keyboard when it is sitting flat on the desk, assuming the area of the keyboard is about 0.035 square meters? Well, if pressure is equal to force divided by area, then the force applied is the pressure times the area, or 100,000 pascals, or newtons per square centimeter, 10 newtons per square centimeter, times 0.035 square meters is going to give you a force of about 3,500 newtons. Quite a big force. Or let's take a look at the problem of the sleepy fisherman. A fisherman with a mass of 75 kilograms falls asleep on his four-legged chair of mass 5 kilograms. If each leg of the chair has a surface area of 2.5 times 10 to the minus 4 square meters in contact with the ground, what is the average pressure exerted by the fisherman and chair on the ground? Well, the force applied is going to be the force of gravity. So our pressure, which is force over area, is going to be total mass times the acceleration due to gravity, the weight, divided by the area in contact. Mass is going to be 75 kilograms plus 5 kilograms, the chair plus the fisherman, times, let's assume the acceleration due to gravity is about 10 meters per second squared, divided by the total area, which is 4 for 4 legs of the chair, times, each has a surface area of 2.5 times 10 to the minus 4 square meters, 80 times 10 divided by 10 times negative 3, about 800,000 pascals. Great. All right, let's take a look at the problem of a scale on a foreign planet. A scale which reads 0 in the vacuum of space is placed on the surface of a foreign planet. On the planet's surface, the scale indicates a force of 10,000 newtons. Calculate the surface area of the scale, given that atmospheric pressure on the surface of the planet is 80,000 pascals. Well, once again, pressure is equal to force over area. We're looking for the area, so area equals force divided by pressure, which will be 10,000 newtons over our pressure of 80,000 pascals, which is going to give us an area of about 0.125 square meters. Here we have a set of conditions, and we want to know Which is the highest pressure and lowest pressure? Let's put them in order. The atmosphere at sea level, well, we know that's about 100,000, or actually 101,325 pascals. A 7,000 kilogram elephant with total area 0.5 square meter in contact with the ground. Well, the elephant's pressure is going to be force over area, which is going to be 7,000 kilograms times 10 meters per second squared, the acceleration due to gravity, divided by that half a square meter, or 140,000 pascals. A lady in high heels with total area 0.005 square meters in contact with the ground. Well, pressure equals force over area, which is going to be 65 times 10 divided by 0.005, or about 130,000 pascals. Or a 1,600 kilogram car with total tire contact area of 0.2 meters squared. That's going to be pressure, force over area, or 1,600 times 10 divided by 0.2, or 80,000 pascals. So if I were going to rank these in order from highest pressure to lowest pressure, I'd start with the elephant, B, the lady in high heels, C, the atmospheric pressure, A, and last, the 1,600 kilogram car, D. How about pressure on a submerged object? The pressure a fluid exerts on an object submerged in that fluid is determined by multiplying the density of the fluid by the depth submerged, all multiplied by the acceleration due to gravity. Call that gauge pressure. It's equal to the density of the fluid times the acceleration due to gravity times the depth submerged, rho gh. If there's also atmospheric pressure above the fluid, such as the situation here on Earth, you can determine the absolute or total pressure by adding in atmospheric pressure, which we typically write as P sub 0, or 100,000 pascals. So the absolute pressure is P0 plus the gauge pressure, or P0 plus rho gh. Again, where P0 is equal to 100,000 pascals. So let's take a look at a gauge pressure problem. Samantha spots buried treasure while scuba diving on her Caribbean vacation. If she descends to a depth of 40 meters to examine the treasure, what gauge pressure will she read on her scuba equipment? Assume the density of seawater is 1025 kilograms per cubic meter. Well, to solve this, let's start out by writing our formula for gauge pressure. That's rho gh, where that's the density of the fluid rho, which is seawater, 1025 kilograms per cubic meter. Acceleration due to gravity, let's assume 10 meters per second squared again. And the depth, 40 meters, so 400 times 1025 should come out to be around 410,000 pascals. All right, let's take it a step further. Samantha spots buried treasure while scuba diving again. She descends to 40 meters to examine the treasure. We want to know the absolute pressure exerted on the diver by the water in the atmosphere. Well, the absolute pressure is equal to atmospheric pressure plus our gauge pressure, which is going to be about 100,000 pascals, plus what we just determined as gauge pressure, 410,000 pascals, for a total absolute pressure of 510,000 pascals. Now let's talk a little bit about Pascal's principle. It says when a force is applied to a contained incompressible fluid, things like water, hydraulic fluid, most fluids we think of are incompressible, or mostly incompressible, the pressure increases equally in all directions throughout that fluid. So if you push down on a fluid and it's in a container where it can't get out, it's incompressible, you're going to have that same force you push down with on all directions of the container, all sides of the container. That's the foundation for hydraulic systems, things like barbershop chairs, or construction equipment, or even car brakes. You've seen in the movies where they cut the brake lines on a car, the fluid leaks out. Now when you start to push on the brakes, they no longer work because you don't have fluid filling that container. And this really works by force multiplication. Let's talk about force multiplication using Pascal's principle. If we apply a force F1 to a piston of some area A1, we create a pressure P1. Now, since this is transmitted through an incompressible fluid in a closed container, we're going to have the pressure on piston A2, the pressure P2 must be equal to F2 over A2. But Pascal's principle says those pressures must be equal. P1 and P2 have to be equal because they're exerted on an incompressible fluid in a closed container. So P1, which is equal to F1 over A1, must be equal to P2, which is F2 over A2. So putting those together, if P1 equals P2, then F1 over A1 equals F2 over A2. Or F2 equals A2 over A1 times F1. We have effectively increased the applied force F1. Of course, the law of conservation of energy can't be violated, so the work done on the system must balance the work done by the system. In this diagram here, the distance over which F1 is applied will be greater than the distance over which F2 is applied by the exact same ratio as that force multiplier, A2 over A1. You'll have to push this piston down further. It will move a lot more, but you get a greater force over here, but with less displacement. You have effectively multiplied the force that you've applied. And you will see that in many different systems. Think of something like a hydraulic car jack. Push down here with the smaller force, get a greater force over here in order to lift up the car. It doesn't move as high, but you get much more force, so you can lift greater weights. Let's take a sample problem of a barber's chair. A barber raises his customer's chair by applying a force of 150 newtons to a hydraulic piston of area 0.01 square meters. If the chair is attached to a piston of area 0.1 square meter, how massive a customer can the chair raise? And let's assume the chair itself has a mass of about 5 kilograms. Well, to solve this problem, let's first determine the force applied to the larger piston. F2, which is going to be A2 over A1, times force 1. Therefore, F2 will equal A2, 0.1 over A1, 0.01, or a ratio of 10 times F1. We're going to need 150 newtons, so this is going to be 10 times 150 newtons, or 1,500 newtons, the largest force applied. So, if F is 1,500 newtons, and that's equal to mg, the weight, then m must equal 1,500 newtons over our acceleration due to gravity, g, 10 meters per second squared, or 150 kilograms. That's got to be divided up between the 5 kilogram chair, leaving you a 145 kilogram customer that you could lift in that chair. Hydraulic systems allowing for force multiplication. Let's take a look at a hydraulic car lift. A hydraulic system is used to lift a 2,000 kilogram vehicle in an auto garage. If the vehicle sits on a piston of area 0.5 square meters and a force is applied to a piston of area 0.03 square meters, what is the minimum force that must be applied to lift the vehicle? Well, once again, in the hydraulic system, P1 equals P2. Therefore, F1 over A1 equals F2 over A2, which implies then that F1 equals A1 over A2 times F2, which will be 0.03 divided by 0.5 times F2. Therefore, F1 equals 0.03 over 0.05. And F2 must be our 2,000 kilograms times 10 meters per second squared, the weight of the car. So that's going to be 0.03, divided by 0.5. times 20,000 or 1,200 newtons must be applied in order to lift that vehicle, equivalent to a weight of 120 kilograms. Let's take a look at the pressure on a penny. A penny with a diameter 19.05 millimeter sits on the bottom of the ocean, seawater, 1025 kilograms per meter cubed for its density, at a depth of 340 meters. What is the force on the penny? Well, let's start out by finding the area of the penny. The area of that penny is going to be pi r squared, where r is going to be half the diameter. So that's pi times 0.009525 meters squared, or 2.85 times 10 to the minus 4 square meters. The absolute pressure, then, is going to be P0 plus rho GH, which is about 100,000 pascals, atmospheric pressure, plus rho 1025, G 10 meters per second squared, times the depth 340 meters, or about 3,585,000 pascals. Now, if pressure is force over area, then the force must be the pressure times the area, or 3,585,000 pascals times the area of the penny, 2.85 times 10 to the minus 4 square meters, for a force of about 1,022 newtons on that penny. Let's take a look at depth in fresh water. A diver's pressure gauge reads 250,000 pascals in fresh water. How deep is the diver? Well, gauge pressure, P, is rho GH. Therefore, H must be equal to the gauge pressure divided by rho G, or 250,000 pascals, over, well, rho for fresh water, 1,000 kilograms per meter cubed, and G, about 10 meters per second squared, gives us a depth of about 25 meters. A pressure gauge reads 350,000 pascals. What is the absolute pressure? Remember, absolute pressure is atmospheric pressure plus gauge pressure, rho GH. So if we want to know the absolute pressure, that's just going to be 100,000 pascals plus the gauge pressure, 350,000 pascals, for a total absolute pressure of 450,000 pascals. Hopefully that gets you a good start on pressure and Pascal's principle. If you need more help or are looking for more information, check out aplusphysics.com. Thanks, and make it a great day.